Alright, hell yeah. Okay, so what we have here is the transformation equations for pure strain. And I swear this has got to be one of the hardest concepts in material mechanics. So even got a couple books here. We got Material Mechanics of Gear. Hell yeah. And then we have Material Mechanics of Hibbler. And so sweet. So they each have their own, way to describe what's going on. This is Hibbler, and then this is gear. But they still just use a diagonal. And so these two videos, this is kind of part two. In part one, I for sure at least went over the transformation equation for the strain with a rotated element. Now what we're going to do is the angle, the shear angle that forms. This angle from, a vertical. That's what we're going to do. So we're going to derive this equation. And I only have an hour, so, but we should be able to go just a lot faster. So there was the big takeaways from the last video is if, let's say we have a beam and we got a lot going on with it, a lot of loads and stuff, and we're just going to take a little point, and we want to know what's going on at that point. And before this, what we have is like, hey, that point might have, well, even a free body diagram. That point might have axial tension or compression forces. It might have in both the vertical and horizontal direction. It might be in tension, it might be in compression. We might have shear forces that are this way and this way. And if we do, this would rotate this element. It would just spin with a dynamics problem. So we have to balance that with a countering couple. And then obviously the shear forces could be in the opposite direction as well. So that's kind of the free body diagram. And what this element is, it's a three-dimensional cube. And so if we have a force on this face, I'm going to associate that with a pressure. So force divided by the area, that's going to be a force per length squared. This is going to be, and for this would be tau, the shear force. The stress. I'm real bad at the actual lingo. Just because I always want to think of stresses as like forces, because I think those are more tangible. Same thing with, today we're talking about strain, and strain is a change in length, So this is a very tangible quantity, just as force and loads are very tangible. Now what is strain? It's the change in length per the unit length of something. And so same thing with stress. Stress is a force over an area. And this number in materials can only reach a certain quantity. And so if I analyze a material and I get to this number, hey, maybe it's gonna fail. And especially if I analyze it and I get a number that's bigger than the actual strength of the material. Then we have a real issue going on. You want the strength of the material, and then you want to analyze those numbers on stresses, and hopefully those are smaller, even with some factors of safety. Same thing with strain. A steel bar that's 1 meter, that would be 1,000 millimeters, can only change length by 2 millimeters. And it's almost imperceptible. You can't really gauge that with construction materials like steel, concrete, wood. And so, and that's what makes strain also kind of a harder concept to grasp. But the same thing applies. If I know something can only change by 2 millimeters per 1,000 millimeters, which is 0.002, and this is where we get this change in length in meters per initial length. But still, the units on here are a change in length per initial length. And so if I was starting out with, if I only had 500 millimeters, I could only lengthen this length of steel by 1 millimeter. And so this also gets into the, like, what's synonymous? Like, if I have a 1-inch steel bar, strength of steel is 58,000 psi, pounds per inch squared. So I can put a force, a load, if this area is 1 inch squared, I can put a load of 58,000 pounds in tension. But if I only have a 1/2, if this is 1 by 1/2, and this area is 1/2 of an inch squared, and this is the bar that I'm pulling on, I can only pull 29,000 pounds. And when I pull 29,000 pounds over this area, and we talked about tau being the stress or pressure on where your force, like this is your shear force, and then here is the direction of your area. The area of a face is always perpendicular to that face, so this would be an area vector. This would be the force vector. Now these are perpendicular, where if you have tension and compression, hey, here's my area. The area is perpendicular. This is the area vector, and guess what? This would be the force vector. This would be the tension vector, and they're in the same direction. So then our stress isn't this term tau. This is for shear, but we use sigma, and that's going to be for compression and tension. And so with steel, we still have that number of 58,000. We can't exceed that. But in both of these scenarios, 29,000 on 1/2 of an inch. So what's the units on normal compression, normal stress? This is called normal stress, where it's in two different directions. We have tension and we have compression. Compression is just a negative number. So we're going to have tension on these, and the units on this is force per area. So that's force per length squared, and that's so what we have is we want to know this in both scenarios, and we got a force of 29,000, an area of 0.5. That's the same thing as 1/2. So dividing by a fraction, just multiply by the inverse, and we're multiplying this by 2. So we get 58,000. We get 58,000 psi, pounds per square inch, on this cross section, which is right at the limit. And on this one, our normal stress and tension is force divided by area, which is 58,000 divided by 1. And so both of these are going to have the same pressure. And so that is very similar to this concept. So this is how we can compare apples and oranges. If I have this chunk of material, hey, I can put a load on it until I get a pressure of this max pressure. So even if I have some really thin wire, I can only put a load on it until I get this same number. So in all cases, this number is going to be the same. And so that's synonymous with strain. I'm going to have very different lengths, whether this is the Golden Gate Bridge or like a climbing carabiner. You know what I mean? One can stretch feet, maybe even meters. I don't even know. But the other can only stretch fractions of a millimeter. You know what I mean? But what's the similar? Because we just said in here, the two things that were similar was this max number. So even for two different lengths, the max strain is still going to be the same. If it's steel, it can only see a strain of 0.002, which is a ratio. It's dimensionless units, but it's length per length, and that's going to be a change in length per initial length. So, and then that gets into like, hey, this is an equation of three things. Strain is change in length per initial length, and so I could rearrange for change in length as strain times initial length. This one gets hella used in our derivation. And probably an unlikely candidate to get used would be initial length is change in length divided by strain. But at least you have three different an equation with 3 different values, and so you can rearrange and solve for 3 different terms. So if I have a material that has a max strain, you know what I mean, I would say change in length max is equal to the max strain for steel. It's going to be 0.002 times my initial length. You know what I mean? Initial length doesn't get the symbol max, but you know what I mean? Whatever my initial length is going to determine what my change in length is. So here I have 2 millimeters. I can have 2 millimeters of change in length on this. I could have 1 millimeter here. What's the same on both of those? Is the strain. Strain is change in length, 2, divided by 1,000. That's going to be the same number as change in length of 1 divided by 500. Alright, so that's kind of the intro, and now we are going to start doing this derivation. Booyah. Okay, so I guess, you know what I mean, that was good, but I guess what I was starting to do was this, is if I have some sort of loads on a beam, you know, we got a lot of loads going on and a lot, whatever, let's see. Oh yeah, and I talked about how in this chapter we don't want to get too excited right away. You know what I mean? So we have this idea of like, hey, maybe I just know that this thing's in tension this way, maybe compression this way, and maybe it does have some shear forces, and we can actually write this as a this is going to be shear stress, and this is going to be normal stress. So we have normal stress in the x, normal stress in the y, and a shear in the xy plane. Okay, sweet. And you know what I mean? What's going to happen when we pull on this way? When we pull on this way, this little box is going to lengthen. If we compress this box, you know, in the vertical direction, this little box is going to shorten. You know what I mean? So this box goes to this length, and now this box goes to like squatter. It used to be up there. And what happens when we shear something? And let's draw some bigger pictures, because this isn't quite so obvious. And even in the textbooks, you might be like, well, why are they doing something? So what I would do is if we're going to shear this with a shear stress here and here, and an opposing shear stress here and here. And oh, we should back up, because I think we get that, hey, I have a force here, and then it has to be an opposing force here, and that force is going to be on a face, and so this force on a face, the shear is going to be force divided by area, which is the shear divided by the area. And so, cool. So we're going to have and here's my coordinate system, x, y. This is going to be an x face, and it's going to be in the positive x direction. And then this is going to be, so shear xy is a shear on the positive x face, so the x is positive, and it's in the positive y direction. When both of these are positive, this is associated with positive shear. If both of these are negative, over here, this is tau xy2, where we have the negative x face in the negative y direction. That's still positive shear. Now on this face, oh, and then, so why I did this is because if I have an upward force, it has to be balanced by a downward force. But this is going to cause this thing to rotate. And so we need a balancing force the other way. So I'm going to put an arrow here. And but we have to, if this is associated with a force diagram, you know what I mean, it's not traveling this way, so we have to balance that with a force going this way. And this is the y face, so we have shear on the y face in the positive x direction. So this is positive y face, positive x direction. This is shear yx still, but it's the negative y face in the negative x direction. So this is still associated with a positive shear. Because the areas are the same on all these faces, and then the pressures, pressure times area, has to be associated with a force. So if I do have a force up, force up, and then a force down, and then a force this way and this way, then these forces are the same, and therefore the pressures are the same. So tau xy is equal to tau yx, and you know what I mean? You could just right off the bat just call everything tau xy. And you don't even need to do that. Typically, you just do this. You know what I mean? You go this, 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 and then you just say tau xy. And why? And this is gonna. And what's the shape that's gonna happen? That's kind of the next thing we're gonna look at. And I think the easiest way to do this diagram of what the shape would look like is to draw a box xy coordinate and then fix this origin. With this fixed origin, I know that this side is going to go up and this side is going to go over. This side's going to go down and this side's going to go that way, but we still have to have some. It's useful because even this isn't going to be the full picture of what's happening. I'm sure it's like actually rotating about the center, but we still have to have some way to visualize and quantify shear. So what we're going to say is that this length is moving up. So I'm just going to draw two arrows. So this point goes to there, this point goes to there. And that's kind of the easiest way to draw shear. This line moves, you know what I mean, just the same amount this way. Cool. So now this will connect the dots here. I mean, if you want to get a head start. But then where do we go up here? Well, these 2 points have to be the same. So I'm just going to box it in. And these points are going to be right there. So then this diamond shape is, by connecting the dots, this is what's going to happen. And all these angles are the same. If I come in here, and so right here I'm gonna say this is gamma divided by 2. So that's the sign convention. It's gonna be the shear, and this is shear strain. Shear strain is an angle. It's an angle in radians, and all of these are going to be gamma divided by 2. And so what we're interested in is the fact that this box used to have a 90-degree corner, and now it doesn't. This corner is now less than 90, and it's 90 minus this angle and that angle. So it's 90 minus gamma divided by 2, 90 minus gamma divided by 2. This is the shear strain, so it's 90 minus the shear strain, and we could call this the shear strain in the xy plane because it's diamond shaping in the xy plane. It's not diamond shaping out of the board or anything like that. And so we just have 90 minus gamma in the xy plane. That is what's happening to this corner, and we're going to associate that with positive. And then you can see that this corner is also, this is a reduction. So that's what we're seeing. So positive shear is where you have the diamond shape happening, and I would call this the first quadrant, second quadrant, you know, if I'm drawing my quadrants. And all the shape is still in the first quadrant. If we had negative shear, my shape's going to be right here. This is going to be down, over, up, over. I'm going to fix my point right there. This thing is going to go here. This line is going to shift that way. So it's kind of the easiest way to do it. We know that these 2 points have to be the same. I'm going to box it in and place it right there. And now I have my diamond shape. But this is one way you can get this diamond shape perfect every time. And then so still, the same angles form, you know what I mean, from the vertical and horizontal. Everything is gamma divided by 2. And you can see that this new angle is going to be 90 plus gamma divided by 2 plus gamma divided by 2. So this angle is going to be 90 plus both of those other angles. So what happens is what we want is like, well, you know, I just want gamma. I just want this shear strain in the xy as an angle in radians, and I want just to do that very visually And so what we're going to do is we're just going to take this element and then just shift it down so this line is just right here. When we do that, this goes flat. So if I did that, I would just have this shape happening. So that's all we're doing for our... so now this is gamma, this is gamma. And so all I did was take kind of a truer definition of shear, kind of what's happening, because we're these lengths don't change, and we're getting kind of a change in this whole thing is kind of rotating a little bit and diamond shaping, where here it doesn't look like it's not rotating about this x-axis because we just because we said so. I mean, it's basically like saying, well, let's just say our x-axis is right there, and then we get that same shape. And you know, and no textbook has even shown like a picture of like, well, what if you had your axes right in the middle? Like, what would that shape look like? Because even fixing it about this axis and saying that your diamond shape is something like this, well, you know, why is that point fixed? You know, I mean, just by convention, and just to make it look. All right, so now we can probably, and like I said, I only have an hour, so we need to kind of focus and get here. Okay, so what we're going to have is a rotated element. And I'm trying to get back to this beam, where, hey, my square is drawn with an xy coordinate. And problems of this nature are going to be like, hey, this little element, whether it's a cube, and typically they're just going to show you this face because nothing is going on in this direction. And for these, this is a huge disclaimer because this whole chapter is in plane strain. So we're going to have a change in length in the x, a change in length in the y, and an angle rotation about the xy plane. But no angle rotations about, you know, into the board, out of the board, and in the other, you know, the other two planes, I guess. And we don't have any change in length in the z, which we know from if I have this cube and I'm putting it in tension, this is the x, y, and this is the z plane. If I'm putting this cube in tension, sure, it's going to lengthen, but then it's also going to squat. It's going to compress in this direction and this direction. And so that's going to compress, that's going to narrow in this z direction. But for these problems, we have to be very specific and say it's not doing that. So one way that we do that is we set up problems with like two parallel plates. So if I did this, and so we have two parallel steel plates, and guess what? I'm going to put a chunk of rubber right here, and then I'm going to say that this is the y plane, this is the x plane, and then this way, you know, is the z. So this would be the negative z, and you can see that if I put a pressure, if I put a force down on here, a force down over this area is going to be a normal stress where you have pressure, and that's going to cause a bulging out. We're going to have a change in length in the x direction. We're obviously pushing down on it. We're going to have a change in length in the y direction. And so that's why I get used to just saying change in length, because I don't know, I just don't think people have this idea of strain just like built in. I think, even for me, I think it would take a decade for me to be like, strain. Okay, now I got it. But so this is what happened. This is the problems that have to occur, is where we just don't have any change in length in this direction. And so, yeah, it's kind of fast. I haven't done any of the problems yet. You know, I've just kind of I'm just interested in the derivation and trying to do it in a hell yeah format. Okay, so they're going to give us the strain in the x and the strain in the y, and then the change in length. So, I mean, you're talking about a differential element. It's going to, and this is the x, y, z. So it's going to change in length. This was the initial length, and we're just going to call this a small little element. So it's going to have a dx and a dy. and it's part of a cube that also has a dz. But hey, this little element is going to bulge out, and it's going to change in length in this x direction. It's also going to change in length in the y. And we're just going to say a positive, if this is going to be a positive value, it gets bigger. Cool. So those are the things that are going to happen. And a positive value here is it's going to do that. And we're fixing this this line along the x-axis, and we're just rotating it out an angle. Cool. So those are the three things that are going to happen to this element. And the cool thing is we're going to superimpose. We're going to see what one does, and then we can superimpose the results, into just kind of one equation. And then for these problems, we're given these three values based on, this electrical. It doesn't have to be more than 1/8 of an inch, but we have this little electrical grid, and then we're going to glue it to our beam. So this is actually kind of what happens. And we run electricity through wires, and these wires have a known thickness. And if I have axial tension in this direction, guess what's going to happen to these wires? They're going to change in length in this direction. That's going to be a strain in that direction. But while it's changing length, Poisson's ratio says that wire is going to reduce. It's going to get thinner. You know what I mean? And when small wires get thinner, their electrical resistance is very sensitive. And so you know what I mean? So I can know how much strain was caused, because strain in this direction is causing a change in diameter in the other kind of two directions. You know what I mean? If this is the diameter, I have a change in this is the x direction. I have a change in the y and a change in the z. And so those changes are causing that diameter to change. So the diameter is going to reduce, and I can measure that electrically. So these problems come into a category where we're going to be given, what's going to happen. So this element is, we know it's going to change in this direction, and it's going to shear in that direction. What we are interested in, and then, even if we're interested in it or not, what we want to know is like, hey, so we did this, and we got the strains in the x, y, and then rotated. Are those numbers representative of the biggest thing that's going to happen? Because we just said that we have to go to our books and for steel, like, hey, this is the number for shear stress, where we have forces that are, at perpendicular to the area vectors. You know what I mean? So if you have, things, and then those are, and the definition is very vague. It's just a force that causes a tendency for two parts of the material to move past one another. So this molecule is right in line with that molecule, and pretty soon these molecules are going to be down here, these molecules are going to be down there. Where compression and tension is more obvious. It's like, hey, if this is in tension, these molecules are just going to get farther apart. If it's in compression, those molecules are just going to get closer together. And so those are the three things, and we have a value. So tension, compression, and we can only have a certain number before those materials will fail. And the same thing for strain. I can only have changes in length in the x and y direction, and a change in angle. Because even that is just like, well, if this value is for like the forces that are going to cause this, well, this motion causes that angle to form. And so that is probably one of the underlooked things in material mechanics, is like, I can know, if I have a 1-inch steel bar, I can know that I can put 58,000 pounds. That's one way. Or I can just measure its initial length and then measure its change in length. So let's say I don't know what load I'm putting on, but then I have 1,000 millimeters and I see 2 millimeters of lengthening. If I could accurately measure that, I'd be like, well, that's 58,000. And so I'm glad I said that, because that is the most overlooked thing about like putting these gauges on. The second you put a gauge on, and if it's steel and you're reading .002, well, you're getting 58,000 psi in tension and compression in that zone. Alright, hell yeah. So that was about just a 5-minute explanation that says, if I know the strains in the X and Y, and then the shears about the XY plane, when my object was taking, you know, if I just measured this, if I put the strain gauges on kind of just in a XY orientation, but what would be the case if I took that strain gauge and then epoxied it, or however they adhese it, and then I just put it at a 20-degree angle? Like, would these numbers change? And the answer is yes. And then there's going to be a rotation where we're going to get these numbers to be max. Maybe some are min, but that's not what we're interested in. We're interested in, hey, if there's a max number for this, we want to know. And that's going to be associated with some sort of angle. And there's going to be a max number with this, same thing with an angle. Honestly, you should just care less about the angle, but just care more about the who cares method is like, hey, this number could be bigger. And I'm sorry, we're talking about strain here. So the strain, the actual strain that's happening in a particular direction is, you know what I mean? So then you kind of just have two values. You have a strain in a particular direction, and then you have an angle rotation in a particular orientation. And those are going to be two numbers. There's going to be a max number for this and a max number for that. So yeah, this thing is going to give you a strain in this, and then a perpendicular to it. Those are the two numbers that you're going to get, and then a rotation of that element. Yeah, you could glue this on 360 different ways, you know what I mean, in a circle, and run the experiment, and you're going to get, at some point, you're going to get the strain to be the biggest number, and at some point you're going to get the angle to be the biggest number. And so that is what we're in. And then so yeah, and I'm glad I said that, even though we have strain in the X and strain in the Y, I mean, you're probably just interested in when one of those is max. You know what I mean? So so that keeps it kind of simple. Like, this video is not going to go into the Mohr circle or anything. We just kind of want to we just want to have that, like, the who cares perspective of, like, yes, if my strain gauge said this is a number, this is a number, and this is a number, and these numbers could be double. Let's say they could be double to triple, and it's going to be dependent. Like, this number is going to influence that number, you know what I mean, and vice versa. But yeah, that would be significant. If I get a reading on all three of these, and one of them is a 2x multiple, then that's significant. So that's what the whole idea of getting an equation based on this angle, because then we can take a derivative, or just plug this into your calculator and graph it and see where this angle is going to be the max. All right, hell yeah. All right, booyah. So now I hopefully can get here just a little bit faster. When we are changing lengths in this X direction, so this is going to be the X direction, or the Y direction, cool, this thing's going to go here. So let's say I drew, let's say all strains are going to be half. So if this is halfway, hey, the change in length is half. So this thing, and that's visual. So what is strain? Change in length divided by initial length. And if I say my strain is 0.5, then what's that going to be? 0.5. My initial length, let's just say, is 1. And then change in length. Well, this change in length has to be 0.5. So there you go. So my change in length is 0.5. My initial length is 1. My strain is 0.5. Cool. And so, so what happens if this shape is going to go to this shape? You know what I mean? Is going to increase by 50% or a strain of 0.5. And I draw a line dead center. If I just paint this line on, where's that line going to be on here? Well, it's going to be right in the middle. And this is a very, and so let's keep doing some more of these. If I have this shape, and it's going to strain, you know, halfway, it's going to come out here. So this is how far it's going to go in the X. And guess what? I'm going to paint on a diagonal line. So what's going to happen to that diagonal line down here? Well, it's still going to be a straight diagonal line. So I think this is kind of a good flow to get into. And same thing in the X direction. If I have a strain of half in this direction, it's going to be a shape like that. And it wouldn't matter where I put the diagonal lines or even a center. You know what I mean? Heck yeah. Those lines are going to look like that. Cool. So now we kind of have that. Same thing as if I have this square and it's actually going to, I'm going to go halfway this way and then also halfway this way. So this shape is going to go half and then half. And then let's say I painted a circle, you know what I mean, on here. You know, and then strained it. What's going to happen is that circle is going to be in the same location. So this is where none of the things that we just showed right here were a function of anything about the material, about the atoms, you know, the strength of them, the bonding. This was just straight geometry. Where, but it does require the material to be homogeneous. It's got to be the same material with the same properties. But I guess it doesn't matter if the properties are like linear like a spring or Play-Doh. You know what I mean? Where it just starts to gush. You know what I mean? So if I took this circle and you know what I mean? And then let go, you know what I mean? So if this was a spring and I took this circle and then tensioned it and it got to be this circle and then let go and it just went right back to this circle. That's the idea of linearly elastic. Every molecule goes back to the same location. But even if you get into plastic zones where like, hey, now this circle kind of Play-Doh'd into this shape and it's kind of stuck into this shape. Nothing funky is going on. You know what I mean? So that is one of the things that the text talks about, and that's a decent one to, like stuff like that is like you might not catch on your first go around because the whole idea is to just get equations. Alright, so that is kind of the thing that you need to keep in mind. And so, and the same thing when we change angles. If this thing changes an angle to here, you know what I mean? That's going to be that shear strain. And so now my new angle is going to be like this. What happens if I paint a diagonal line on? Well, that diagonal line is just going to be right there. Cool. And this diagonal line for sure changed in length. And so we're going to use that knowledge. Now, check this out. Yeah, this is good. Because if I go back to this X, and I know it's can double to this way. What happens if I just draw a straight line? I paint a straight line like this, and then that straight line is going to be like right there. What happened to that straight line? That straight line changed in length. So that straight line for sure changed in length. And this straight line is giving you a visual representation of strain. Change in length divided by initial length. This is the initial length of that line. This is the final length final. And so I know the change in length because that's length final minus length initial. And then this is length initial. And so strain can be really simple, and I would always break it down into an equation like this: change in length, initial length, length final. Yeah, and so how about over here? If I have this length, let's do one more, because I'm going to take that same shape, and then I'm going to go kind of halfway. So it was like here, and I'm going to go strain of 0.5. What if I drew a diagonal line on here? I just said that this, changed in length by, the change in length was 0.5, the initial length was 1, and then so the strain on here was 0.5. 0.5 divided by 1. Cool. So now here, this thing still had a strain in the x direction. This diagonal line is now like this. Is the change in length on this diagonal line 0.5? Is the initial length on that diagonal line 1? Or, and I don't even know, you know what I mean? Like, I don't think so. That's the whole reason that we, in part 1, that we had a transformation. Because you're just like, hey, add a diagonal. I don't know. Like, it could be, is it more? Is it less? And so let's just use really simple geometry to find out. So this is 1, this is 1, this is 1. Pythagorean's theorem says 1 squared plus 1 squared square root of 1 squared. You should always do, even on the simple ones, like 1 squared plus 1 squared, square root that. Well, that's going to be the square root of 2. Oh yeah, no duh. And so that's the initial length right here. I'm going to say this is now 1.5, and this is 1. Okay, so that length is going to be 1 squared plus 1.5 squared. And that's going to be the length final. You know what I mean? 1.5 squared is 3 halves squared. You know what I mean? This is kind of fun to get into. Yeah, 1 half is 3 divided by 2. 1.5 is 3 divided by 2. If we're squaring it, we're going to square top and bottom. That's the same thing as 3 squared divided by 2 squared, which is 9 divided by 4. And then we're going to add 1, which is 4 fourths plus 9 fourths. So we got square root of 13. Square root of 13 fourths. And then I can play that same game. That's the square root of 13 divided by square root of 4. It's really fun to use kind of those rules of... but anyway, and then the square root of 4 is 2. So we have square root 13 divided by 2. We'll just do a double check. 1 plus 1.5 squared. And then the square root of 13 divided by 2. So hell yeah. And I'm going to store that as my calculator into x. And then we got the square root of 2. Store that as a or whatever. So let's see our change in length. Our change in length is going to be this minus the square root of 2. So this is our change in length. I'm going to say that's c. And then so our strain on here. Our strain is going to be the change in length divided by our initial length. So that's going to be 0.3885 divided by the square root of 2. So we're just going to divide that by the square root of 2. And my strain right here is only 0.274. So if this line had a strain of 0.5, this line had a strain of 0.274. So there you go. It was much less. All right, hell yeah. But that was in one case where we just had a change in length in the x direction. If we have a change in length in the x, a strain in the x, a strain in the y, and a rotation about the xy plane, those three elements can add up. So if I did rotate this, maybe I'm rotating it this way and then lengthening it this way. So now this diagonal lines up here, and maybe I get a strain that's 2. You know what I mean? So initially I just had a strain in the x, or a strain of 1. Sorry, if something doubles, it's a strain of 1. So if I had a strain in the x of 0.5 and a strain in the y of 0.5, and then I get a strain about this new axis to be like 0.7, the square root of 2 or something. Well, hey, that might be my new biggest max, and so that's kind of what we're interested in. And if this shifts this way as well, hey, this line is now going to lengthen even farther. And so those three things about this rotated axis are now pretty significant. Alright, hell yeah. So, and I probably should just try to burn this out, or maybe do it in 2 parts. But anyway, so here is the proof, and this is how I like to draw it. I mean, I don't have to juggle back and forth, you know, as long as I keep moving. So I think we can do this. So hell yeah. So we're gonna have our best way to do this is draw your element, just kind of like the textbooks. You're going to have a dy and a dx. So you're going to have kind of a rectangle. It's better to draw your rectangle longer, and then because you're going to have a tangent to this angle. So this angle is a little bit narrower than 90, and then we're going to come up like this. And so all we're doing is saying if I rotate, so now I know that this can change, and I can have a strain in this direction, a strain in the y, so keep that in mind. Strain in the x, strain in the y, and then a rotation about the xy plane. Rotation, change in the x, change in the y. What we're interested in is if I rotate this up a particular angle, maybe that change in this direction is going to be hella, and then I want to know that, you know what I mean? And so, and I think it's useful to just rotate this up. So we're going to come up here and then draw that element in. And then, so here's my rotated element. But I don't know anything about the change in this direction. That's why we have to use only the knowledge of the change in this way, the change in that way. And so, and kind of painting on those diagonal lines. But now I am interested, so this is my new dx term, you know what I mean? This rotated up to here. And this is different than the textbooks. The textbooks are going to actually connect this point with that point and call that dx prime. I'm not going to do that for this video. We can do other videos where we compare, you know, because I want to do these more quickly, where you're just like, okay, here's this compared to that. But these videos are just kind of the slow roll process of, like, you know what I mean, just making sure we're all on the same page every step of the way. So this rotates up. I'm going to say it's just that same dimension dx. But again, I only know things that are happening this way. And so let me draw one more picture. Is if I drew this picture in and then boxed it in like this. And then I said I had a strain in the x direction. That was half. So this is going to go over here. Yeah, this is super cool because none of the textbooks do this. And I think, like, if all you stick around for is this, and I kind of just busted all the way through, like, what's going to happen? Like, and this point is going to stay the same. This point is going to stay the same over there. But proportionally, these points are going to move. You know what I mean? So now I have this. Would these be 90? No, it has to move. You know what I mean? If I said like this point is right at halfway, like that point has to be at halfway. If this point is just a little bit farther than a quarter of the way, it has to be there. You know what I mean? This is a very fascinating approach. This point has to be there. And now it doesn't even matter. So there you go. So I don't think these remain 90. So there you go. So that kind of shows like what would be taking place when you have and so what we had was like, hey, this was our dx, and now we can analyze, you know, because I know that I'm going to have this happening in the x. Hey, I can now measure this length using geometry compared to that length, and I can find the strain, and we're going to call this the x1 direction, y1, or x1, x prime, y prime, however you want to do that. But now I can know the strain in this x prime direction. All right, booyah. So the simplest way to do this, to make the geometry just hella more simple, is to drop down. Consider this your hypotenuse, and then drop down some lengths. So this length right here is now dx cosine theta. This length right here is dx sine theta. And so now for this shape, I know it's going to increase in this length due to the strain in the EX. So let's write the strain equations. Change in length divided by initial length. So the other equation we need is the change in length is strain times the initial length. So this is the equation that we'll be using throughout. So if I have this strain in the X, this is what's going to happen. And we're just going to analyze one at a time and see how this line changes. Ultimately, we're going to say, hey, we want to change. We want to know the strain in the X prime direction. This is Y prime. And that's going to be the change in length in the X prime direction divided by the initial length in the X prime direction. The initial length is dx, and that's what is going to really make this just so much easier. Alright, so this change in length is going to be the strain in the X times the initial length in the X. Now it's not this. This is my initial length in the X. So we have dx cosine theta. And then we got to come up here. This is where this gets kind of tricky because we have a very small triangle. Now for this, I'm going to say if this is theta, I'm going to put a dot. That's going to be my complementary angle, like theta and phi. So if I have a right triangle and this is theta, this is, draw a little bit bigger. This is theta, this is going to be phi. Because these triangles get small, I'm going to say an angle, if I do that, that's going to be, that's associated with theta. If I do a dot, that is going to be associated with phi. So theta and phi. So right here, I can be like, hey, and there's a lot of different ways to find, if this is the horizontal and this is the horizontal, same slope, this is going to be my angle. So we're good to go on this one. And now what I'm interested in, what I'm doing is I'm going to treat this as my hypotenuse. So I need to drop this down, which is, just doing your rotated coordinates. So this is the x prime, y prime, and then I can see that this goes there and this goes there. All right, hell yeah. I'm going to try to go faster because I just realized that, we talked about the change in length this way. We're not even doing that in this video. What we're interested in is, and I apologize. So if this is my initial shape, I'm interested to see if this shape goes like this. And that's already given in the problem. We already know that it does that. These are the three given parameters. What I'm really interested in is if is when we rotate this shape to here, I want to know how it shears, and these shear angles happen on this rotated plane. So this is going to be x1, x prime, y prime, shear strain in this new rotated, and that number could be bigger. That's the whole point of doing this, is that this number might be analytically bigger. And so so here's our new shape. I'm really interested in this angle change. And so a positive angle change would be that this moves this way, and then that this line moves that way. So if I get the shape to look like that, you know what I mean? And so, here's my new shape. Then I'm going to add both of these angles up, and that's going to be associated with gamma x1, y1. So that is what we're doing. And so we have rotated this up, and so what I'm interested in is how this line changes. How it pivots from here and then rotates. So from the strain in the x is going to cause this, and so still, this is our element that we rotated. This is dy and then dx. But I can't analyze it at this rotation, so I kind of have to box it in this way. But I'm only analyzing this line right here so far. And I want to know if it changes angles. And it does because this smaller box moves out here, this proportion, and this point on this line is now right here. So that's what's going to take place, is that line is right there. And so this, in the books, they're going to call this alpha. And I want to know what that is. So we use the equation, because this is in radians, we use the equation that radians times radius is something normal, and that's arc length. And so if this is my angle in radians, my radius of this is going to be dx. And then the arc length is this component right there. So I know this is my hypotenuse. If this is theta, then this arc length is hypotenuse sine theta. So hell yeah. So now I'm going to write in this arc length. It's going to be this value. Strain in the x dx cosine theta. And this is the hypotenuse right there. And then sine theta. So that's my first alpha term. And guess what direction it's in? It's not making this positive shear. This is actually making this negative shear. So I mean, so now you have to put a sign on this of negative. All right, hell yeah. So it's going to get busy, but and I got to probably, start my day and stuff. But we're going to now do the strain in the y. So this thing is going to come up to here. And this value right here is going to be, from our equation, change in length is going to be the strain in the y. So we have strain in the y times the initial length, which is dx sine theta. And so now it's cool that we don't even have to use dy and do some, I think overly complicated trigonometry. We can just say, hey, that is the change in length with respect to x. And because right here, to get alpha, all we had to do is just factor out the dx. You know what I mean? So now we have, this is the value for alpha, for that change in angle. When we have the strain in the y, here's our new change in length. And so this point goes up there. This happens. This is our next alpha term. You can call this alpha 1, or you could call this alpha strain in the x. This could be alpha strain in the y, just associated. And this is my new hypotenuse. What I'm going to do is kind of draw in the rotated coordinates in the y1, x1. And then if this is the hypotenuse, these are the two components, right triangle. That's going to be the hardest part about that, but just make sure that, hey, this length is a hypotenuse because it's not in the x1, y1 direction. And so we're drawing those components in. If this is theta from a horizontal, this is the other thing, is that from the vertical, this has to be theta. Because if I have a 90-degree triangle right here, this has to be alpha. And then if I have another 90-degree triangle over here, this has to be alpha. Because this is 90. So if this line is 180 and I already chiseled out a 90, these two have to add up to 90, and so we have to have complementary angles. So now I know that from the horizontal in this positive slope direction, this is theta. I could go the other direction, it's still a positive slope, but that's theta. From the vertical, because a perpendicular has an opposite slope, the slope is negative. From the perpendicular, I have to have a negative slope. And then this is going to be my angle theta. So hell yeah. So I have a perpendicular. This has to be a negative. So this is theta. And then there's the theta. Okay. The arc length is right here. So we have the so the arc length is hypotenuse cosine theta, which is this. So now let's do our second alpha term. So radians times radius. The radius is still the same. So alpha times dx is going to be, and I'm not worried about sine right now. I'm just doing the, so radians times radius is this arc length. This arc length is strain in the y, dx sine theta. And then we're going to have the cosine theta. And that is this arc length. Now, the reason why this is arc length is because these are really small angles. So this straight section of line, even though you would have a curved section, the straight section of line is an approximation that is pretty much 100%, unless this thing's made out of rubber and stuff. You're going to get a very close approximation. So that's, for these derivations, you have to do that approximation. I mean, or they do, and then so that's what these classic equations come from. All right, hell yeah. So then you have this, and you can factor out the dx, and we have the alpha term. Okay, so there's going to be one more term, and that's because this thing shears. This original block, has a shear angle of shear strain due to this angle. And we're going to use that same radians times radius. This is going to be in radians. And so we want to know this change in direct. And when this changes to over here, hey, this line now becomes over here. And let's get a sign on this one. This last one made this line move up that way. And that's going to be associated with a positive shear. So this is positive. This distance is going to be radians. And this is strain. This is going to be gamma xy. That's in radians. The radius is dx sine theta. So I have this. So I know what this is. This is gamma xy dx sine theta. This is going to be my hypotenuse. I'm going to do the rotated angles. This is a component and this is a component. This is the component of the arc length. So this next alpha term, radians times radius, is this arc length. And this arc length is going to be the hypotenuse and then sine theta. So this is going to be gamma xy dx sine theta, which is sine theta squared. And this caused a negative, factor out the dx, and this angle caused a negative shear. So those are your alpha terms. So I'm just going to write them down, and hopefully we can get the heck on. So my first alpha term is going to be associated with the shear in the x direction. So we have cosine theta, sine theta. The second alpha term is going to be associated, and it's going to be positive, with the normal strain in the y direction. And then the third alpha term is going to be negative, gamma xy sine squared theta. Okay, I think it might be useful to, and it's good to be able to kind of draw these halfway fast, rotated angle, and then we're going to have our shape up here. And now what I'm interested in is I want to know, because this, if it shears this way, is going to be that gamma x1, y1. And so I want to know that angle. And so I need to know what's happening over here. We just had this diagonal, and so the resultant of these angles plus are going to be like a alpha resultant, and that's either going to be in the positive shear direction or negative, depending on what our inputs are. But that's only half, like or not half, but it's only a partial of what the shear is. The shear is going to be the reduction. This is a 90-degree angle. The definition of shear is going to be the reduction, the total reduction of angle. So alpha is going to be the reduction of angle on this side, or increase. It could be a positive shear or a negative shear. But now we have to come over here to do this diagonal. All we have to, and so this is dy, this is dx. All we have to do is just drop down and make a rectangle, and all those same things are going to apply. this rectangle is going to do that same strain in the x, it's going to do the same strain in the y, and it's going to do the same, like this shape in the shear. Its initial lengths are going to be different. This is theta, so this is going to be dy sine theta. This is going to be dy cosine theta. And then the only other equation is just know that, and then the angles that are going to occur, we're going to call this, over here we're going to say these angles are beta. And I'll go with the sign convention of the textbooks. I think it's maddening, just because it just adds one extra layer of complexity. I don't know. You would probably do it with modeling, maybe if you put it into a computer and stuff. But hell yeah, so let's do it. So we're going to have this strain in the x, and so this length is going to be ex times the initial length, dy sine theta. Okay, so we are interested in this line changing length, and so that's where you could say that this is rotating. Like, it's kind of nice to fix this point. It doesn't matter though. If this line rotates, even if it rotates about the center, this line is changing angle. And so this could be useful. Even though we have positive shear strain in the x, that's the same thing as making it positive this way. You know what I mean? If this initial rectangle bulges out this way, that's going to be the same. This is still going to be strain in the x dy sine theta. Any increase in width is associated with a positive strain in the x direction. So now this diagonal, especially if we have a pivot point here, this line is now going to be right there, and we have this angle beta to occur. And so I know what this this is going to be my hypotenuse. Again, kind of draw in the coordinates, and then so here is the two. If this is the hypotenuse, these are the legs of the right triangle, and then. From the horizontal, this is theta, so there's my theta right there. I'm interested in this arc length, so this is going to be the hypotenuse cosine theta. So hell yeah, so radians times radius, we're going to say this is beta times dy, that's the radius on this one, is equal to radians times radius is arc length, so that's ex dy sine theta cosine theta. Booyah. And now we need a convention of whether this is positive or negative. I mean, it rotated it that way, which would be negative shear. But in the textbooks, they're going to call, because the positive shear was due to a positive counterclockwise rotation, which is a right-hand rule rotation. They're going to say that an angle rotation this way is going to be positive beta. But that's going to be associated with negative shear. So isn't that crazy? You know what I mean? So we're going to get our beta term as a positive number, but know that that's associated with a negative shear. So our total shear in the x prime, y prime direction is going to be alpha minus beta. And I just think that's dumb, because visually we can be like, hey, if this rotates that way, it's going to be positive, and this is going to be negative. But we're going to call counterclockwise right-hand rule rotations. So hell yeah, this is going to be positive, and we have beta is ex dy sine theta cosine theta for that one. All right, so now we're going to increase this in the y due to the strain in the y. This line is going to be up here. This is the angle that forms. This is the hypotenuse. This is strain in the y times the initial length, dy cosine theta. This is the hypotenuse. We're going to draw our rotated axes. From the vertical, you know what I mean? If this is from the horizontal, from the vertical, and this is a positive slope, from the vertical, I'm going to have a negative slope. And so, hell yeah, this is theta. So that's kind of the fastest way to do that. Kind of the bow tie method. Keep a idea of from the horizontal, positive slope, perpendicular, I'm going to have a negative slope. And then so this has to be my theta. So there you go. So theta's right there. And I'm interested in this arc length. That's going to be a sine component. So I'm going to have this times the sine. This is my hypotenuse. I'm going to have hypotenuse sine theta. All right, so the angle beta, radians times radius, dy, is going to be this hypotenuse times sine, the sine component of it. And then you just have to factor out the dy. Sorry I didn't factor out this dy right there, but hell yeah, factor out the dy. So now this, and then this angle was going to be negative. You know what I mean? Because we rotated this way. All right, hell yeah. And then so for this next one, the angle is going to be this way. We're going to rotate it negative. And so this distance right here is because we had this shape and it shears about this initial value they give us. The shear in the xy plane, we're going to have gamma xy. Radians times radius is this. So we're going to have gamma xy times dy cosine theta. That's this, and then this is going to be a hypotenuse. We're going to draw our rotated axes, and then I can see, and then same thing from the horizontal. This is theta at positive slope. This is theta. So then my all right, hell yeah. So let's see. So it's going to rotate this way. It's going to be a negative rotation. If here's my hypotenuse, this component is going to be my arc length. You know what I mean? Because this is my beta now. And so this arc length is going to be that hypotenuse cosine. So cool. So I'm going to have radians, beta, radians times radius, beta times dy is this hypotenuse cosine of the angle. So I'm going to have cosine squared. So we're going to have gamma xy dy cosine theta squared. And you just see it's just super fast to cancel out the dy's. Oh, and then this was going to be a negative rotation. And it's just kind of good to go back to check your rotation. So if this was my initial square, when I increase it this way, this is going to have a positive rotation. If I increase it this way, this rotated that way, negative. If I shear it in the positive direction, this line goes to this way, that's going to be a negative rotation. All right, so now we're just good to go. So beta 1, 2, and 3. And we're still saying that these are all clockwise rotations as positive. So the total shear still is going to be alpha minus beta. But beta, due to the shear in the, sorry, I don't know why I'm calling it shear. Normal strain in the x is shear strain, normal shear strain in the x, sine theta, cosine theta. Negative, normal strain in the y, cosine theta, sine theta. Negative, shear strain about the xy plane. Again, these three terms are given for these problems. You know what I mean? That's going to be negative shear in the xy plane, cosine squared theta. So now we can just put these together, and we can say that shear in the x1, y1 is going to be alpha minus beta. So we're going to have minus. Yeah, you just have these. I don't even know why I'm, you know what I mean? Hey, then you're just going to have those, and then just a sign change on this. You know what I mean? You're going to have these. Well, I guess we better write it out. Normal xy, cosine theta, sine theta, plus normal normal strain in the y direction, sine theta, cosine theta, minus shear strain about the xy plane, sine squared theta, and now we're going to have minus the normal strain about the x axes, sine theta, cosine theta, plus normal strain in the y direction, cosine theta, sine theta, plus shear strain about the xy plane, cosine squared theta. And then hell yeah, so we did it. You know what I mean? And like I need to actually probably go. But you know what I mean? This looks different than this, but this is the first place that you can throw this into your calculator, find maxes and minimums. The only thing that they do is divide by 2, and then, oh, and I printed off the wrong, like, yes, this is the same. I think we did it right here. See how we have a sine theta, cosine theta, sine theta, cosine theta, and we're going to have a negative EX plus EY, just a little trickiness going on right there. And because we have two, sorry about, yes, so that's oh, no, we're right. Yeah, this whole thing is, look at these two terms happen twice. So we're going to have 2 of those, we're going to have 2 of those, and then we're going to have 1 of these each. And then, so hell yeah, so we can actually factor out, we had 2 of those, so we can factor out the half. But over here, when we take this as a function of just half of the shear, we're going to have these 2 terms, but then halved. So what's common to both of them is the shear and the xy. We're going to have a negative sine squared theta and then a positive cosine. And I did print out, and then what we're going to do is you're going to get it in this form. And all you're going to do is use trigonomic identities to not have a sine theta, cosine theta, or sines, and cosines squared, because you won't be able to differentiate those. So what we're going to do is trigonomic identities to get it in terms of just a simple sine of an angle and a cosine of an angle. It's a 2 theta, but now we can differentiate this and find a max and a minimum. But hell yeah. So anyway, I gotta go. But I think that pretty much concludes part 2, and I think that was pretty decent. Alright, so thanks for joining me, and that's a video.